This is a recording of a live webinar held on September 25th, 2024, the last in our three-part series entitled Expert Insights Food Safety. Check out the previous two parts on cleaning and food-grade lubricants on our channel, where you can also find product demonstrations, instructional guides, and more. Click the link in the description to learn more, or to follow us on LinkedIn to be kept in the loop of upcoming events.
Good afternoon, everyone. My name is Carmen Seibert, and I will be your host for today's webinar. I am the current product line manager for food and beverage here at DuBois. I wanted to start off by saying thank you to everyone for joining us, not only today, but the past 2 weeks as well. For everyone that's just hopping in for the first time, this is the third and final session that we will be holding under the food and beverage webinar series. I wanted to thank everyone for joining us. And if you're curious, the previous two are currently available on our YouTube page. So if you find yourself wanting to know more or you didn't catch them the first time, please check us out on YouTube and give those first two a listen. There's some great information on those about open plant cleaning, cleaning in place, and food grade lubricants. As always, there's a Q&A section built into the end for any questions that may come up. So if any point during the presentation you think of some, please feel free to direct those to the Q&A tab. I'll be cycling through those to pose them to Brandon at the end. Speaking of, Brandon Mahler is our expert for today. Brandon is somewhat of a veteran here at DuBois. He's been with the company for 19 years, and he's worked in various roles, including technical support as an R&D chemist. However, now he's in the role of R&D manager. Brandon specializes in adopting technologies from other industries and applying them as innovative solutions for unique problems. Most impressively is the author of 4 patents and a member of TABI. Without further ado, I will be passing the microphone to him to kick us off.
All right. Thanks, Carmen. Appreciate the introduction. Defoaming. I think in order to better understand how defoaming works, it is important to first understand how foam is generated. All right, so what is foam? So essentially, foam is just a colloidal system, so a mixture of particles within different phases that are dispersed or come into contact with one another. So the key components, especially for our application areas, are gas, which is generally air, and liquid. All right, so how is foam formed? It's formed when there's a large interface between that gas phase and the liquid phase. So basically what happens is, you mix your gas and your liquid together, and then these molecules, right, they start dispersing within one another. Well, the liquid molecules at this interface, they want to bond with the other liquid molecules within the bulk solution. So they want to hold on to each other, right? They don't want to disperse further into the gas phase. So that creates a cohesive force, right, which is called surface tension. It creates this strong film, or what's called a lamella, around the gas. The gas is therefore trapped, right? So you've got this film, right? The gas is trapped within that. And that's what forms the bubbles. So you get some bubble formation as a result. Okay, so foam in and of itself is not necessarily an issue. So, for example, in pure liquids such as water, when these bubbles are formed, these gas bubbles are obviously they're less dense than the water phase that they're sort of trapped in, right? So as they're less dense, they tend to rise to the surface of the solution. As they contact the surface of that solution, the lamella becomes thinner and thinner, and eventually those cohesive forces are not strong enough to keep it together, and it bursts. So in this environment, for pure liquids, foam is not an issue. So when is foam an issue? It's when it becomes stable, right? When there's something in there, there's an additional material in this solution to stabilize those gas bubbles, so they don't want to thin out and they don't want to burst. These materials, which are essential for that, are called surface active substances or surfactants. Okay, so the key properties of these surfactants is they have two unique qualities. They have a hydrophilic or polar head, which is attracted to the water or to the liquid side, or in this case, the water side of the phase mixture. And then they also have a hydrophobic or nonpolar tail, which is repelled by the water. Okay, so these surfactants, what happens in this solution, in this mixture, is they tend to orient themselves around the lamella because the heads like to attach to other water or other polar solutions, but then the tails, which don't like the water, tend to orient themselves within these air bubbles. So you've got your air bubble that you can see here in the diagram. It's surrounded by these surfactants, and what those surfactants do is they stabilize that air bubble. We'll go and get into the mechanism of that here in a couple of slides, but surfactants, they can come from either natural sources or synthetic sources. So some examples that you can see here of natural surfactants, especially within the food industry, are lecithins, proteins, and starches. Some examples of synthetic surfactants. These are molecules produced from non-renewable resources, such as like a linear alcohol oxalate. You see more synthetic surfactants on like the cleaner development side, formulation side. All right, so how does this work? How does these surfactants stabilize these air bubbles and generate foam? So at first thought, you might think, well, it just will strengthen that lamella, right? It'll make that area, that surface interface between the liquid molecules and the air molecules, right? Just make it stronger. But that's not really actually the case. It more stabilizes the lamella, and that's called the Marangoni effect. And so what happens just naturally, as this lamella is stressed or is stretched, the surface tension reduces. So you can see here in the diagram, the top picture, where you can see in the middle there, the lamella is thinning out. So that weakens that area of the bubble, and naturally with no surfactants, eventually that's going to pop, right? But what happens is these surfactant molecules, they want to transport from like a higher surface energy state to a lower surface energy state to balance out the system, right? They like that equilibrium. Okay, so you can see how it goes from not as many surfactant molecules in that thin, more than in the thicker areas, then want to move to that thin part. What happens is it sort of stabilizes or rethickens that lamella, and in a sense strengthens it, but more stabilizes it. Okay, so we all know that foam can be a major issue in industrial applications. Okay, so there's a number of issues that it can cause. These are just a few of them I've listed. They can cause problem or product contamination. You've got sort of poor quality or low grade product that's coming out of that's being generated. You could have product that's out of spec. It's hard to sell, or you have to reuse it, or just can't get the value out of it. Besides just the product contamination, though, there's also other issues. These include environmental pollution. I'm sure we've seen examples of runoff where the foam can just travel, just pour out off of the machine, just run into your sewers, or run across the floor, or even down, driveways, get outside of the facility, and cause a major impact that way. Not only the pollution on the side of whatever is being processed and whatever the defoamer chemistry is, but foam's a great carrier of stuff, so it picks up stuff as it goes along, and can cause problems that way. If it gets bad enough, oftentimes machines have to be shut down to clean up the mess. What that causes is production loss, for sure, right? You're not making product at that point. And then you also have to account for the time and cost of cleaning up the system, getting it ready and acceptable to restart and make a good product again. Okay, so how do we control this foam? How do we mitigate these problems that can occur? Well, firstly, foam control is essential. It is not really feasible to eliminate these foam stabilizing surfactants in industrial processing. So if we're in a, for example, potato processing plant, we can't just say, oh, we'll eliminate the starch from the system, right? That's not going to work. So instead, we've got to control it. And really, there's two main application areas for foam control. One, we can prevent the foam from occurring in the first place. That's referred to as antifoam. Two, once the foam is able to build up, then we want to break it down or destroy it as quickly as possible. And that's more of the defoamer applications. Now, a lot of times those two words are used interchangeably, right, often, so got to be careful on how we use them, but essentially that's how we differentiate. All right, so when we control the foam, there's two unique mechanisms in order to do that. Oftentimes they're used together as sort of a 1-2 punch. But the first mechanism is we can do it chemically. And that involves the 3-step process that you see here. Just generally, what you have to do is the defoamer has to enter into that foam lamella, right? It's got to be able to transfer, from wherever it's being applied and get onto the surface of the foam or air bubble. Okay, after it does that, then it's got to spread into that air, liquid, and surfactant interface. And then finally, once it's spread, it's got to be able to destabilize that lamella so that it can rupture and the bubble can pop. And then we'll go through these steps a little bit more specifically here now. Okay, so the first step, entering the lamella. Okay, so the defoamer, like I said, must have that strong tendency to migrate to the air-water surfactant interface. And what this does is, otherwise, it's not going to pop the bubbles if it can't get there. Okay, so it requires a proper hydrophilic lipophilic balance, or HLB. So basically, that balance has got to be it's got to be targeted specifically. The problem is if the defoamer is too lipophilic, right? If it's too nonpolar, it's going to be insoluble in that water medium. So you can apply it to your system, right? And so if it's too hydrophobic, it's not going to migrate into that water and transport to the foam. It's just going to sort of sit there, right? Sit there like, oil on top of a water solution. And maybe you'll get some defoaming like right in that specific area, but you're not going to be able to effectively defoam your entire system. Okay. So the opposite can be true too. If it's too hydrophilic, that can also be a problem. So if it's too polar, the defoamer particles just sort of stay with the water phase, and then again they can't reach into the bubbles. So that's kind of what you see here in the photo, in the picture, with those 3 defoamer particles that are just sort of floating in the water. They can, unlike the previous example, they can disperse well into your system, but if they never penetrate into the lamella, there's going to be no efficacy for defoamer. Okay, so once we've got that proper HLB so that the defoamer particle can penetrate into that interface, the next step is it's got to spread out across across the lamella. Okay, it can't just sit there. It's got to spread, and what the spreading does is it sort of pushes the surface, the surfactants that stabilize the foam, it sort of pushes them more away from each other. It does this through what's called low cohesion energy density. And basically, just what that means is that these surfactants, which want to migrate, like we said, from a higher surface energy state to a lower surface energy state, which, you know, through this Marangoni effect, right, it will sort of even out or thicken up the lamella. What the defoamer does when it spreads across is it prevents it. So all of a sudden, these surfactants that stabilize the foam do not want to transfer through that chemistry to thicken the lamella, and eventually we're mitigating that Marangoni effect. So obviously, then it comes to reason that the third effect is the combination of the penetration and the spreading causes quick thinning of the lamella, and that will eventually cause it to collapse, and then the bubbles break, and then you can have effective. That's how you get your effective foam control. Okay, so the second mechanism is a physical mechanism of breaking down the bubbles. So just sort of intuitively, a physical mechanism just involves like the physical destruction of the lamella. So these are often hydrophobic solid particles that just run into that lamella surface and just puncture it, right? Break it down, and then you can get the bubbles to pop that way. So this is especially effective in combination with the chemical mechanism of breaking down the bubbles that we previously discussed, right? Because you can see here in the photo that if you thin up the lamella, right, and you cause sort of weak points in there, that when that hydrophobic particle runs into it, it sort of scatters these, you can see these green surface surfactant foam stabilizers, right? Sort of scatters those molecules, right? So they can help form these weak spots, and then the thinner the lamella is, the more like susceptible those weak spots are to bursting. So it can be a pretty effective 1-2 punch to control the foam. Okay, so there are a number of different types of defoamers that can be used to effectively control the foam in your system. And there needs to be a number because there's so many different types of materials that can cause the foam in the first place. And they're different across all different types of raw materials, the way that they're produced, the environments, and the on the machines, and then the systems. So because of that, we can employ a number of different types of defoamers are important to have. They're basically categorized into 3 main groups. There's silicone defoamers, there's oil-based defoamers, and there's polymeric defoamers. Okay, so silicones these are based on silicone oils, and they often include hydrophobic silica with it. So you've got the chemical way of breaking down the foam added with the physical way of breaking down the foam. So here you can see is the structure of polydimethyl siloxane. That's sort of the most common silicone oil that's used in defoamer chemistry. You can see what some hydrophobic silica looks like, just physical particles that are often mixed in with the silicone oils or even reacted with in order to provide, that the physical effect as well. Okay, so as with any of these types of defoamers, there's advantages and disadvantages of using the silicones. Okay, so the big advantage is it's got a very low surface tension. So what that does is it just makes the whole process faster, right? There's that rapid spreading into and across the gas, liquid, and surfactant interface, which certainly facilitates the weakening of the lamella. And then just generally, silicones are pretty good. They're pretty good from like a use and environment perspective. They're pretty resilient in a broad range of application conditions, such as temperature. They're also pretty resistant to acids and salts, which some of these others aren't. And it's got a pretty good human and environmental toxicity profile. So from an EH&S standpoint, it can be, pretty useful to use as silicone. The main disadvantage is, though, that it's very hydrophobic. Okay, so that's good in breaking down the bubbles, but it can also be rough because it will just have an affinity for any hydrophobic surface in your system, right? So you add a defoamer, if it's add a silicone defoamer, and if it's not properly applied, that free silicone can plate out onto all types of hydrophobic machine surfaces. It can carry over into the product if you're making if there's any sort of oils or anything that you're dealing with in the product, and it can cause all sorts of issues for machine runnability or process runnability. Also, because they're hydrophobic, they can be difficult to formulate. They have to be formulated. You can't just add a silicone as is because it's so hydrophobic, it's not going to migrate to your foam very well. So in order to facilitate that, you've got to formulate with it, and that can be difficult. So it needs a dispersant to help migrate. And if it's not properly formulated, right, the efficacy can be diminished pretty easily. Okay, the second type of defoamer that's common is an oil-based defoamer. Now, these are like non-silicone oil-based, and often they contain the oil carrier, which is the active defoamer part. Again, hydrophobic particles to help physically break down the foam. And again, these need emulsifiers too, right? You just can't add oil to a system. It's not going to effectively migrate across the foaming issue. Also, these emulsifiers are important to help disperse the hydrophobic particles in the oil. So you have a consistent, useful product as you're applying it. There's different types of base oils that can be used for these type of products. Most common are white mineral oil, or a synthetic type of oil, or more natural oils such as canola oil. You can see here the different types of fatty acids that can be used in this type of formulation. All right, so some of the advantages of oil-based, they can have a good cost to performance ratio, so you can get good value there. For the synthetic oil specifically, they tend to have higher thermal stabilities, so you can use them in hotter systems without breaking down. They don't deteriorate as easy, and there's no odor associated with the mineral oils, so that's always an advantage. For the renewable, for the more natural oils, some advantages are they can have very high efficiencies, and then they can have more minimal environmental impacts. Okay, some disadvantages. Sometimes these oils can have negative impacts on the end product that you're making. So here is an example in like a coating application. If you use oil-based defoamers, that can negatively impact the gloss parameter of that. So that's something to be aware of. Also, like in food applications, right, you don't want to, if you're not careful on how you apply them, you can sort of oil out your whatever you're trying to make at the end. That can cause certainly quality issues. The white mineral oils, sourced from petroleum, it's non-renewable, so that can be an issue sometimes. Unfortunately, on the natural oil side, because they have they decompose at a lower temperature, they can start to generate pretty foul odors pretty quickly. So you've got to be careful with that. All right, and then the third type of defoamer is polymeric-based defoamers. So these, again, are non-silicone polymers. The most common example is the polyglycols, where we're building surfactants, or we're building these materials that have both the hydrophilic component. In the example below, this is so these are EOPOs, right? So they use ethylene oxide as the hydrophilic component, and then the hydrophobic component is the propylene oxide. And then you have so that's your tail. So they can be effective defoamers as well. So the advantages, again, they can be highly efficient. They're often cheaper than silicone-based defoamers. Cool thing about these is they can be tailored to specific application conditions because they're synthetic, so they can be processed using the very specific monomers and designed with specific molecular weights to target the specific defoamer problem that's that the customer is having. They can be targeted toward both water-based systems and oil-based systems because they have that flexibility. Some disadvantages of the polymeric-based are they can be difficult to formulate with. So again, need to have the capacity to build these very specifically and very, very much on target. And then a lot of them need to be in specific temperature conditions to work properly. So as they're added, at room temperature, or if it's just like mildly at certain temperatures, right, these surfactants, these polymer-based defoamers, they can hold into the water too well, right? So a lot of times you have to heat them, put more energy into the system. That sort of flips their characteristic, and their hydrophobic ends come out of solution in temperature and provide the defoaming characteristics, but they've got to reach a certain temperature often to do that. All right, so now that we have the different types of defoamers, these defoamer materials, they have to be often have to be formulated into end-use products. So all defoamer formulations, they include a number of different types of chemistries. You have your carrier fluids. These are important because they make the product addition easier and the faster distribution to where the foam problem is occurring, and they can lower the product cost. So often these carrier fluids are water or sometimes organic solvents too. Then you have your active ingredients that we just discussed, right? Liquids, you've got your silicones or mineral oils or oils or polymers. And then you also have your solids, which can be hydrophobic silica, they can be waxes, fatty acids, any sort of hydrophobic material that will help break down the foam as well. Additionally, a lot of the defoamer compositions also include some stabilizing agents, make sure everything goes together and makes a stable solution. Preservatives, a lot of these chemistries are prime environments for bugs to grow in, so we want to prevent that from happening. And then also they can include surfactants, which again can help penetrate into the lamella to make it more, make the defoamer more, better, more efficient. All right, really key in formulating a defoamer is we've got to get the right particle droplet size. That is going to optimize our application. So we've kind of been discussing this throughout the presentation, but the size of the insoluble part of the defoamer solution when added to the system is critical. And this is based on the balance of the material compatibility and the material incompatibility, okay? So we've got our active materials, whether it's silicones or oils or polymers, right? We've built it into, we're building into this formulation, right? And we've got to build it in a way that when we apply it to our system, it's going to both migrate to the areas of concern, right, across all of the foam problem, right? But then it's also got to be able to break down the foam once it gets there. So here's some examples of some issues that we can have if the particle droplet size isn't correct. If it's too small, right, we have, it's too compatible with water, right? It holds within the water too much. It's over emulsified, we call that. And what that does is, even though it causes good wetting, right, it's able to migrate across the whole system. It's got very weak defoaming, right, because it wants to stay with the water. It doesn't want to go to that lumella and to weaken it, right? On the other end, if our particle droplet sizes are too large, right, the defoamer, when we apply it, the active material is just going to sink, right? It's called cratering, right? It's just going to hit the surface of the solution. It's going to fall, and then it'll, break down the foam of like sort of whatever it runs into in its path, but it's not going to spread, and it's not going to get into the full foaming environment. So again, we've got causes poor substrate wetting. Even though it's a strong defoamer, it's only going to defoam a small area of what we're looking to control. Okay, the other important factor of these formulations is product stability. And you guys know, if we can have the best chemistry and we can have the best application, but if the product isn't formulated correctly, it doesn't really matter, right? We're not going to be able to get what we need to where it needs to go. And defoamers, they offer like a really unique problem for product stability, because we need to create the formula to balance out, right, our material compatibility and material incompatibility, right? But we need to do that in a way that is going to be something that holds up in a tote or a drum or whatever packaging is used for the product. So the key to this is we got to determine the proper HLB to emulsify these incompatible materials. So we've got our carrier oils, or we've got our water, right? We've got our we've got our non-polar or oil part of the product. We've got to combine them into a stable formula. So here you can see some examples of oil and water components that are mixed at different HLBs. You can see on the left-hand side, the higher the HLB, so we get up to 13. We've got that split there, where at the bottom you have mostly water and a little bit of active material, and then on the top, that more opaque white section, right, that's more concentrated material. So if you've got that sitting in your packaging and you're drawing products from the bottom of your container, you're going to have pretty weak defoaming until you get up to that more white layer. That's not an effective way of applying product. Now on the other extreme, at the lower HLB, we have here on the right-hand side a HLB of 7.5. You can see also the product isn't stable, right? In this case, we've got a lot of the bulk solution as the water containing with a lot of active ingredients, but you have a clear oil layer at the top, right, that hasn't been emulsified. Again, you can see all sorts of problems with this, and if we're pumping this into the system, it's not going to be, effective in doing what we want it to. You can see here at sort of in the middle of the photo, right, we've got a system at HLB 9, and we can see that sort of targets the right HLB in order for this to be a homogeneous solution where the product is stable, right, only one phase. We can draw from the top, the bottom, wherever we need to draw, and it's going to provide consistent, useful product efficacy throughout the entire volume. Now, a special note with defoamers is this sort of hazy, cloudy, opaque product is vital for good defoamer. We can't make a clear product, right? If we make a clear product, that means that all of the hydrophobic components of that product are highly emulsified and soluble in the water carrier. When that gets applied, it's just going to stay with the water. So we need some of this insolubility in order to be effective, but it's got to disperse evenly throughout the whole product. So that's the key to a good defoamer formulation as far as product stability goes. Okay, so once we have all of the chemistries that we need to build this product, right? We have the right HLB down that we know it's going to be stable. There are also some important points in how we manufacture this product so that it remains stable. And three key components in that manufacturing are temperature, the type of blades that are used in the mixing process, and the time that we're mixing it for. So basically, all of these three conditions are important because they control the ability of the active materials, the hydrophobic materials in the solution to break up and properly disperse into their liquid carriers. So temperature, as you increase the temperature of the solution, right, you add more, that adds more energy into the mixing process, right? That is going to more effectively thin out any of the oil or hydrophobic material in there. Once it gets thin, it's easier for these emulsifiers to work to stabilize the formula. Okay, mixing blades. Here you can see we've got a couple of different examples of mixers. These are very specifically used in defoamer manufacturing. On the left hand, we have what are called homogenizers. And basically, that's got a mixing paddle that's enclosed in a sort of containment that's got small holes drilled through it. So what that does is it takes the mixture, right, and then the rotating blade forces the components in that mixture through these small holes. So that breaks down the oil into much smaller particle droplets. And then once those are small, again, they're easier to emulsify. We can get that particle droplet size at the size that we want so that we can create that stable formula. Another way of doing it is using a cow's mixer. You can see on the right here, you can see this is a blade with teeth that are oriented up and down. And this, does sort of the same thing in a different way, where it just sort of chops up the oil, right? Chops up the oil again in the smaller droplet sizes, again, which makes it easier to emulsify and build the proper stable formula. And of course, time is always important, right? In this case, it's very important because you've got to optimize it, right? Too little time, and you won't be able to emulsify it as well. But then the opposite could be true too. If you hold these too long into the kettle, oftentimes you can build your emulsification package that is too great, and then you can actually solubilize the oil, which will really negatively affect its performance in the end application. Okay, so we have the different types of defoamers. We have the different ways they work, how they're built, and good stable products that are ready to use in the application. But oftentimes there needs to be another step before we go and we determine, we make a judgment about which of these products will work most effectively. Because, especially on the food side, right? Because the way food processing works, all of the different, feedstocks and conditions of the processing facility it's hard to reproduce and make sort of a one size or one product fits all product. So a lot of times it's useful to do some lab evaluation before, prior to recommending products or trialing products or making those decisions. And these lab evaluations, there are a number of different types of them, and they sort of measure different mechanisms of it. And it's not often too difficult to bring in the actual specific foaming, whatever foaming issues are in the process, to bring that foaming media into the lab and then run some defoamer tests on it. And then there's a couple of common defoamer evaluation techniques that will focus both on the foam knockdown, right? So breaking down the foam, and then what's called hold down, which means we measure its ability to prevent foam from building again. So here are two standard ways of lab evaluation that are used. Graduate cylinder, where you essentially just put the foaming medium in a graduate cylinder at a certain volume. Then you add your defoamer chemistry. Then you cap your defoamer and you sort of invert the graduate cylinder up and down, a set number of times. In our lab, we do it 10 times, right? And what you have is you have your liquid phase, initially, you have your defoamer, and then that inversion sort of aerates the system, right? It causes that, it brings in that second phase, so you have your all your key components now to generate your foam. And then what you can do is after the set number of inversions, you put the graduate cylinder back on the lab bench, and then you just initially measure the foam height using the marks on the graduate cylinder. And then you can actually measure over time the ability of the defoamer to first prevent the foam from forming. But if it does form, right, how long does it take to break it down? So within a 2 or 3 minute test, sometimes the defoamer acts, within the first 15 seconds to break it down. Other times it takes a minute or two to break it down. Other times it's ineffective and won't break it down at all. So it's kind of a good, quick, easy way of evaluating different defoamer products. You can see here that there's actually an ASTM method using just common kitchen blenders to do the same thing. So you just add your foaming media, your liquid, add your defoamer, and then turning on the mixer aerates the system, puts in that second phase, and then you've got your foam generation. Again, you can measure how well the defoamer is in breaking down the foam that's generated. Okay, the third way to evaluate defoamer products, and one that we use here at DuBois in our lab, is we use a recirculation rig. So you can see in the photo, the reason I like using it is it's more of a dynamic evaluation. It can measure both direct injection and surface applications. And then it can also measure the ability to not only knock the foam down, but also prevent the foam from regenerating. So here you can see, it's just a simple, recirculation system. We've got a pump that's built into the flow cycle, and then that's connected to a graduate cylinder. So we add the foaming medium into the system, right? We can turn the pump on, and then we have this what's labeled air liquid intake port. So it's just a ball valve, right? As you open up the ball valve, you bring in the air, right? It gets pulled in through, because we've got a Venturi tube set right underneath it, right? So you've got the differential pressures, right? Pulls the air in, and then you're adding that second phase again, and then you can start seeing your the foam build up in the graduate cylinder. So as it builds up, right, we can inject our defoamer chemistry directly into the port which would, mimic what you do for like a direct injection application, or you can actually drip it on top of the graduate cylinder if you have like a surface application for it, right? So that defoamer, as soon as you inject it, you can start a timer, right? And you can see how quickly and how effectively the defoamer can lower the foam. So we've got the graduate cylinder mark. It's very easy to read the foam level at certain intervals. So ideally, the defoamer will knock the foam down. You can measure that. And then as you continue to run the system, recirculate the solution through, you can see whether sometimes that foam will start building again, right? So the defoamer will be effective in knocking it down, but not preventing it from reforming. So you can measure both that knockdown and then how quickly, if at all, it builds back up. So that can be a useful way of differentiating the different defoamer products that are in contention for the end use application. Okay, so on the food application side, we've got a number of defoamer products that we can offer. Here is a list that we call our signature line. This is kind of what we recommend for the different applications for the different processes in the food line. So here, just to go through them a little bit, the SD10, this is our 10% silicone emulsion. This is something that you'll find a lot out there. A lot of companies make silicone emulsions, but again, not all 10% silicone products are going to work the same, right? Because they've got to be built in to that, aqueous system. And the way of doing that is very different from manufacturer to manufacturer, right? And so, so it's important just not think that one 10% silicone isn't going to work the same as a different 10% silicone, right? A lot goes into that. The PD200, that's recommended for any sort of water-based processing system. That is one of our polymeric defoamers. It also includes some hydrophobic silica, so we've got that 1-2 punch there we talked about. And then the final three products here, the OD260, 208WF, and BD361 are all oil-based defoamers. You can see the different application areas we recommend them in. The OD stands for organic defoamer, so often any manufacturing facility that makes, organic certified products, this would be a useful in those type. The BD361 also uses an oil base, and it's got some hydrophilic silica in it as well to do the physical and chemical defoaming mechanism. So it can be very effective in these application areas as listed. Okay, so BD361, we just sort of went over the chemical makeup of that. Here's a case study where you can see some of the details here on the screen, where we had a potato chip manufacturer that was using a silicone-based defoamer. They were applying it in 2 different locations, and it really wasn't effective in controlling the foam, right? They needed to use a lot of it, right? Heavy dosages. We've talked about the disadvantages. The more silicone you put into something, the more it can negatively affect other parts of the system. They were seeing significant environmental ramifications, and then with their specific product, there was some environmental and toxicity warnings that were associated with the product. So all issues where the customer was looking for an alternative product selection. So the DuBois solution here, you can see we implemented the BD361, a food grade defoamer that is oil-based, and we found you can see the results here that we were able to provide the customer. We were able to reduce their chemical usage by over 70%. Again, because we weren't slugging so much silicone in there, they were able to optimize their process conditions, which was able to improve their costs, and by replacing the silicone to reduce those environmental impacts. So again, even not all defoamer products are the same. They're not all going to work the same. Even the same type are not necessarily going to work the same, right? There's a lot of factors that go into this. So it's really critical that we identify the right type of product, apply it the right way to get the most optimal advantage for controlling the foam.
Awesome. I think that concludes Brandon's portion of the presentation. Thank you so much, Brandon, for all that information. At this time, I will be going through the Q&A tabs. I see we have some lined up, so going to try to cycle through these. And as always, if you think of any as we're going through these, please feel free to submit them. We have about 10 minutes here at the end, so we'll make time for them. The first one comes in. Another question is, am I able to get a certificate for participating in this webinar? Absolutely. As I said the past few times, if you do want one and would like to request that, please send an email over to marketing@duboischemical.com and they will be able to issue you one and get back to you with that information. Our second question is, are antifoams generally continuous adds and defoamers generally spot added as needed, or is that not necessarily accurate? Brandon, I'll pass this one to you.
Okay, yeah. So the way I think about it is, and we talked a little bit about this, but the antifoams they're the application. It's more like an application terminology, right? They're applied to prevent the foam from occurring in the first place. So if you know your process is generating foam, and you want to, control that right up front, right? That's where the antifoams come into place. The defoamers are more, spot applications, like you said, Carmen, where every once in a while, conditions will come together to form or to develop the foaming issue that may not be an issue otherwise, right? And so that's when you would add your defoamer to control that, to knock it down, to make it a more manageable system, so that you can continue to effectively run your system. So now I sort of think of antifoams and defoamers like the mechanisms on how they work are very similar. The chemistry behind it are very similar. It's just more of a difference in application terminology.
Thank you, Brandon. The second one is, does the mechanism change if we're defoaming in an oil-based system rather than a water-based system? For example, if I'm frying potato chips.
Kind of. Well, the mechanism itself doesn't really change, right? So you still need to add a defoamer that's going to migrate to that lamella, right? Going to penetrate into that air liquid surfactant interface, spread, thin out the lamella and pop it that way, right? So that mechanism is still in place, but the actual chemistry to do that can and is very different in the different type of systems, right? So if you have an oil-based system, you need to make sure that HLB of your product, right, is going to be one that's going to migrate through an oil environment, right? Compared to, a water-based environment, that would be a different type of chemistry. So it's important, So the actual mechanism, no, that's the same, but you're going to want to be careful about what product that you're using that's going to be specifically tailored to an oil, potato chip frying system compared to more traditionally water-based system.
Thank you. We have one more here in the queue. Are there food safe options for each of the defoamer types, or are there any that you would never recommend in a food application?
Oh yeah, so we've been talking here about defoamers and their performance mechanisms a little mostly, right? How they work from a purely performance standpoint, but there's lots of other considerations in selecting the correct defoamer product, and often those are like regulatory issues, right? So you got to make sure that it's that the regulations are any sort of specific regulations that the end use manufacturer has, right? That that the product that goes into the defoamer application meets those regulations. There's other like EH&S considerations as well, right? We want to make sure that we're using products that meet those standards. So I'm not sure that I would just make sure that we're conscientious of all of the factors involved that are non-performance that need to be, properly evaluated as well to make sure that the defoamer that is being recommended or is used in the application meets those criteria as well as just the strictly performance criteria.
Thank you, Brandon. I think that was our last one. I'm just scrolling through right now. But everyone that's on here, just know that if you think of any questions after the fact, please feel free to reach out to either Brandon there or myself. We should be able to take that offline and continue these discussions later on. But at that point, that will wrap up our Q&A section. Thank you all so much for joining us these past 3 weeks. As I mentioned, these are uploaded onto our YouTube, so they will always be available to reference, pass along, and even share with anyone who is curious about our options here at DuBois. These presentations have been an excellent way to show off some of our wonderful capabilities we have under the DuBois food and beverage line. But whether you're on today as a customer or representative, I want to say that there is so much more that our F&B team has to offer. So if you'd like to know more about any of the specific topics, or even if there's other things that we can do for you, please reach out to me or any of the associated experts that were featured. Thank you so much again, everyone, for your time, attention, and engagement, and I hope you all have a wonderful rest of your week.